A machine built before the Wright Brothers flew is solving manufacturing problems that $500,000 CNC centers refuse to touch. What this 126-year-old mill knows about cutting metal might just rewrite everything we thought we knew about obsolete technology. Pittsburgh, Pennsylvania, March 1983. The bankruptcy auction of Westfield Machine Works unfolded with mechanical efficiency as lots disappeared to salvage dealers and equipment brokers. Walter Morrison watched Lot 23 with detached curiosity, an 1898 Pratt & Whitney horizontal mill, serial number 287A, that looked like it belonged in the Smithsonian rather than a working factory. The auctioneer's voice barely changed tone when announcing the machine. Built 1898, fully operational according to plant records, weighs approximately 11,000 pounds. Do I hear $200? The room remained silent. These auctions attracted pragmatists hunting for equipment they could flip or utilize, not museum curators collecting industrial antiques. If you want to see more videos about old machines, make sure to subscribe so you never miss another video. At $150, a demolition contractor named Vickers raised his paddle, already calculating the scrap value of the cast iron. Morrison, 48 years old and recently unemployed after Westfield's closure, felt an inexplicable compulsion. His hand went up at $175. Vickers countered with $200. Morrison went to two dealers. His final bid, representing 2 weeks of unemployment benefits, the hammer fell. Morrison now owned a machine older than his grandfather with no clear plan for what to do with it. His wife would have questions he couldn't answer. The machine represented everything modern manufacturing had systematically eliminated over decades of progress. Its 16-foot length consumed floor space that contemporary facilities allocated to 3 or 4 compact machining centers. The elaborate arbor system, with its outboard support arm and precision-bearing assembly, embodied complexity that engineers had spent 60 years simplifying away. Tool changes required complete disassembly of the arbor stack, a process so time-consuming that modern manufacturing management considered it economically indefensible. Morrison had operated similar machines during his apprenticeship in the 1950s, back when horizontal mills still populated factory floors in significant numbers. By 1983, finding anyone under 50 who understood horizontal mill operation had become nearly impossible. Technical schools had purged such content from curricula 15 years earlier, focusing instead on CNC programming and modern machining center operation. The industry consensus was absolute. Horizontal mills represented manufacturing's past, not its future. Every technical metric supported their obsolescence. Vertical mills and CNC machining centers offered superior versatility, faster setup times, smaller footprints, and integration with computer control systems that were transforming production worldwide. Yet something about the 1898 Pratt & Whitney troubled Morrison's intuition. Despite 85 years of existence, the machine showed remarkably little wear. The ways appeared carefully maintained, the arbor showed no scoring, and the drive mechanisms operated with smoothness, suggesting regular, skilled attention. Someone had cared for this machine with dedication that seemed to contradict its supposed obsolescence. What kind of work justified maintaining an 1898 horizontal mill in 1983 when modern technology offered countless superior alternatives? The technical arguments justifying horizontal mills' extinction had accumulated throughout the 1960s and 1970s with mathematical certainty. Dr. Franklin Weber's 1967 textbook, Advanced Machine Tool Economics, presented calculations that became industry gospel. His analysis demonstrated that horizontal mill operation violated every principle of lean manufacturing that was revolutionizing American factories. Setup times formed the foundation of Weber's argument. Preparing a horizontal mill for production required assembling the arbor stack, selecting appropriate spacers, positioning cutters, tramming the arbor to eliminate runout, and verifying alignment across the entire length. Experienced machinists needed 40 minutes minimum for straightforward setups. Complex gang cutter arrangements consumed 2 hours or more. Modern vertical machining centers completed comparable setups in 6 minutes using quick-change tool holders. The time differential translated directly to cost. A horizontal mill sitting idle during setup generated zero revenue while consuming floor space and overhead allocation. Manufacturing efficiency experts calculated that horizontal mills spent 23% of available time in setup mode compared to 4% for vertical machining centers. Floor space economics reinforced the mathematical case. Industrial real estate cost $18 per square foot annually in major manufacturing centers by 1980. A typical horizontal mill occupied 180 square feet, including operator access space. 3 vertical machining centers fit within 160 square feet, while providing greater combined capability. The space efficiency advantage alone justified replacing horizontal mills, even when the machines remained mechanically sound. Labor efficiency arguments proved equally damning. Horizontal mill operation demanded specialized knowledge that bordered on craft rather than technical skill. Machinists needed to understand arbor mechanics, calculate proper spacer sequences, and recognize deflection patterns that affected cut quality. Training a competent horizontal mill operator required 18 months of supervised experience. Vertical machining centers, particularly CNC-equipped models, reduced training time to 3 months. Operators followed programmed instructions rather than relying on accumulated expertise. The knowledge democratization aligned perfectly with manufacturing's shift toward standardized processes and interchangeable labor. Maintenance requirements added another indictment. Horizontal mills contained dozens of precision-fitted components requiring periodic adjustment. The arbor system alone demanded weekly attention, checking bearing clearances, verifying tram accuracy, and ensuring proper lubrication of multiple contact points. Maintenance logs showed horizontal mills consuming 3 times the service hours of equivalent vertical machines. Capital cost comparisons sealed horizontal mills' fate. New vertical machining centers cost $85,000 in 1980 dollars. New horizontal mills, for the rare manufacturers still producing them, commanded $140,000, while offering less versatility. The investment math was inescapable. Vertical configurations delivered superior return on capital deployed. By 1983, these arguments had crystallized into unquestionable industrial wisdom. Horizontal mills belong to manufacturing's past, their continued existence in occasional facilities representing nothing more than institutional inertia from companies slow to modernize. The 1898 Pratt & Whitney that Morrison purchased symbolized obsolete technology that progress had rightfully superseded. Yet if the engineering case was so conclusive, why had someone at Westfield Machine Works maintained that ancient mill with such obvious care right up until bankruptcy? November 1984. Morrison had converted his garage into a modest one-man machine shop after 14 months of unsuccessful job hunting. The 1898 horizontal mill occupied most of the available space, a decision his wife considered somewhere between eccentric and insane. His small vertical mill and aging lathe handled the repair work and small production runs that kept the business marginally solvent. The phone call came from Dennis Hartwell, production manager at Allegheny Forge and Stamping. Hartwell's voice carried the frustrated edge of someone who'd exhausted conventional options. "Walter, I've got a job that 3 shops have already turned down. Wondered if you might take a look before I tell the customer it's impossible." The specification package arrived. By courier, the next morning. Titanium Grade 5 aerospace components, landing gear support brackets for a regional aircraft manufacturer. The parts required machining 6 parallel slots, each 9 inches long, through material thickness of 2 inches. Surface finish specification demanded 32 micro-inches. Dimensional tolerance held to plus 0.008 inches across all 6 slots simultaneously. The challenge wasn't the individual specifications, but their combination. Titanium's properties made it notoriously difficult to machine: high strength, low thermal conductivity, and chemical reactivity with cutting tools at elevated temperatures. The material could work harden during cutting, creating escalating tool wear that destroyed dimensional accuracy. Morrison called the 3 shops that had rejected the job. Their explanations revealed a consistent pattern. Modern CNC machining centers could cut titanium successfully for simple operations, but the support bracket's geometry created insurmountable problems. Cutting 6 parallel slots required multiple setups to access all features. Each setup introduced positioning errors that accumulated beyond tolerance limits. Single setup solutions failed for different reasons. Specialized fixtures that held the part for complete machining in one operation cost $40,000 to design and build, economically viable for production runs of thousands, but absurd for the customer's order of 45 pieces. The shop's CNC machining centers also struggled with titanium's thermal characteristics. The high spindle speeds that made CNC centers efficient for steel and aluminum generated excessive heat in titanium, accelerating tool wear catastrophically. Reducing spindle speed to manage heat increased cutting time to where the job became unprofitable even at the customer's premium pricing. Two shops had attempted test cuts. Both damaged expensive carbide tooling within minutes when titanium work hardening overwhelmed their machine's capabilities. One shop's CNC center suffered spindle-bearing damage from the interrupted cuts and vibration, adding $8,000 in repair costs to their failed bid. Morrison studied the drawings while standing beside the 1898 horizontal mill. The machine's massive arbor could mount all 6 cutters simultaneously for a single-pass operation. The heavy construction might absorb titanium's challenging cutting forces without the vibration that plagued lighter modern machines. But could an 86-year-old machine hold tolerances measured in 10,000ths of an inch while cutting one of the most difficult materials known to manufacturing? Morrison spent 3 days designing the gang cutter setup, drawing on knowledge he hadn't applied in 30 years. The arbor assembly would carry 6 form cutters, each ground to profile for its respective slot. Spacing between cutters needed to match the bracket's geometry precisely. Any error would multiply across 6 simultaneous cuts. He ordered the cutters from a specialized tool, grinding shop, specifying cobalt high-speed steel rather than carbide. Modern engineers favored carbide for titanium's hardness, but Morrison remembered old-timers' wisdom. Cobalt steel cut cooler and tolerated interrupted cuts better. The $2,200 tooling investment represented significant risk for his small operation. The arbor assembly process consumed 2 full days. Morrison selected spacers with micrometers, building the stack with precision that felt more like watchmaking than machining. Each cutter's position underwent verification with dial indicators accurate to 0.01 inches. The tramming operation, ensuring the arbor ran perfectly true across its entire length, took 6 hours alone. His neighbor, a young engineer from a nearby CNC shop, stopped by during the setup. Watching Morrison's painstaking process, he couldn't hide his skepticism. "Walter, I can program a 5-axis machining center to cut those slots in about 2 hours total. Why are you spending days setting up a bio machine from the 1800s? Morrison didn't look up from his indicator readings. "Your 5-axis center costs $500,000 and needs climate-controlled environment. This mill cost me $250 and runs fine in my garage. Besides, your machine already turned this job down." The comment landed with uncomfortable accuracy. The neighbor's shop had been one of the 3 rejections. Setup completion revealed the horizontal mill's fundamental advantage. Once properly configured, the machine could run indefinitely without requiring the reconfiguration that plagued multi-operation CNC approaches. The 6 cutters, mounted and trammed, would maintain their relationship throughout the entire production run. No accumulated positioning error, no fixture complexity, no thermal drift between setups. Morrison's test piece was a chunk of mild steel matching the bracket's dimensions. He needed to verify the setup before risking expensive titanium. The gang cutter assembly bit into steel at 35 surface feet per minute, all 6 slots emerging simultaneously. The mechanical symphony produced by 6 cutters working in synchronized sequence filled the garage with sound that belonged to a different manufacturing era. 12 minutes later, Morrison measured the test piece. 6 parallel slots, each within 0.004 inches of nominal dimension, with surface finish measuring 28 micro-inches. Better than specification, and this was mild steel, easier to machine than titanium, but validating that the setup fundamentals were sound. The neighbor watched Morrison clean the test piece, his expression shifting from skepticism toward something resembling disbelief. "That's actually pretty impressive for a machine built before cars were common." Morrison smiled slightly, already calculating cutting parameters for titanium. "Now comes the part where we find out if old iron can teach new tricks something important." Could a machine designed when manufacturing meant steam power and gaslight handle they. First titanium bracket blank cost $340 in raw material, expensive validation of Morrison's calculations. He mounted the workpiece with deliberate care, using soft aluminum jaw pads to prevent surface damage. The gang cutter assembly, its 6 cobalt steel cutters gleaming with fresh grinding, waited at spindle start position. Morrison set cutting parameters that violated every modern machining textbook. Surface speed, 28 feet per minute, absurdly slow by CNC standards. Feed rate, 0.003 inches per tooth, conservative but calculated to prevent work hardening. Coolant flow, maximum flood coverage using sulfur-based cutting fluid formulated specifically for titanium's thermal properties. The ancient mill's mechanical drive system, designed in an era before variable frequency drives existed, happened to provide exactly the low spindle speeds titanium demanded. Modern machining centers struggled to operate efficiently at such parameters, their high-speed spindles and servo motors optimized for the opposite end of the performance spectrum. Morrison engaged the feed lever. The arbor began rotating with ponderous authority, the 6 cutters approaching titanium that would reveal whether his theory could survive contact with reality. Initial engagement produced a sound distinctly different from the steel test cut, a higher pitch tone as cobalt steel met aerospace-grade titanium. Morrison watched the first chips curl away from each cutter, monitoring their color for signs of excessive heat. The chips emerged dark blue-gray, indicating acceptable cutting temperature. The massive casting that formed the horizontal mill's structure absorbed cutting forces without the vibration that plagued lighter machines. Titanium's tendency to work harden during interrupted cuts, the property that had damaged CNC spindle bearings, disappeared into 11,000 pounds of cast iron thermal mass. 22 minutes after initial engagement, the first bracket emerged complete. 6 parallel slots, machined simultaneously in a single pass exactly as Morrison had envisioned. He carried the part to his inspection table with hands that showed slight tremor, either from tension or the awareness that he was measuring work that might determine his business's survival. The first slot measured 0.0003 inches over nominal. The second, 0.005 under. Third through sixth fell within 0.006 inches total variation. Surface finish measured 31 microinches across all 6 slots. Every specification met or exceeded with margin to spare. Morrison sat down heavily on his shop stool, staring at the completed bracket. An 86-year-old machine, designed before powered flight existed, had just machined aerospace titanium to tolerances that defeated modern CNC centers. The engineering impossibility sat in his hands, tangible proof that obsolete technology could outperform contemporary solutions. He called Hartwell that evening. "Dennis, I can run your brackets. Lead time will be 6 weeks for all 245 pieces. Price is $840 each. That work for your customer?" The pause on the line suggested Hartwell was processing unexpected success after 3 rejections. But what would happen when word spread that someone was solving impossible machining problems with equipment from the Victorian era? The aerospace bracket job transformed Morrison's struggling one-man shop into something unexpected, a destination for manufacturing problems that modern technology couldn't solve. Hartwell mentioned Morrison's success to colleagues facing similar challenges. Within 3 months, Morrison received calls from companies across the industrial Midwest. Each inquiry followed a consistent pattern: complex geometry in difficult materials, tight tolerances across multiple features requiring simultaneous machining. Previous attempts using modern CNC equipment had failed, damaged expensive tooling, or produced quotes so high that projects became economically unfeasible. A defense contractor in Ohio needed turbine blade fixtures machined from Inconel 718, a nickel superalloy that destroyed carbide tooling and work hardened so aggressively that conventional machining often proved impossible. The fixtures required 8 parallel grooves cut simultaneously to maintain dimensional relationship. 3 CNC shops had declined even to quote the work. Morrison's 1898 horizontal mill completed the job using conventional high-speed steel cutters at parameters so conservative that modern manufacturing engineers would consider them absurd. The massive machine absorbed Inconel's punishing cutting forces while maintaining accuracy that CNC centers couldn't match when fighting material that seemed designed specifically to defeat modern tooling. A medical device manufacturer in Michigan sent drawings for surgical instrument components requiring slots through hardened 440C stainless steel. The parts were too small for conventional fixturing, but demanded tolerances of about 0.005 inches. CNC miniature. Machining centers had produced acceptable geometry but couldn't maintain tolerance once stainless steel work hardening accumulated through production runs. The horizontal mill's ability to cut all features simultaneously eliminated the setup-to-setup variation that plagued sequential operations. Morrison completed 200 instruments with statistical process control data, showing improvements in dimensional consistency as production progressed, the opposite of typical tool wear patterns. By late 1985, Morrison had hired 2 machinists and acquired a second horizontal mill, a 1902 Cincinnati Universal model that added indexing capability. His garage shop had become too small, necessitating a move to proper industrial space. The business that began with unemployment benefits and a $250 auction purchase now generated revenue approaching $4,000 annually. The pattern Morrison recognized across diverse jobs revealed horizontal mills' unique capability. When manufacturing required, simultaneously maintaining dimensional relationships across multiple features and difficult materials, the old machines outperformed modern technology. Their massive structure absorbed forces that made CNC centers vibrate. Their mechanical simplicity allowed operating at parameters where electronic controls became problematic. Their gang cutter capability eliminated the accumulated error inherent in sequential operations. Morrison's customers weren't seeking vintage technology from nostalgia or cost savings. They arrived after modern equipment had failed to solve their problems. The horizontal mills represented not a return to the past, but rather a resource that contemporary manufacturing had prematurely discarded. Industry publications began noticing the trend. American Machinist sent a reporter to Morrison's shop in March 1986, producing an article titled, "When Modern Machines Can't: The Unexpected Renaissance of Horizontal Mills." Yet if these machines were so capable, why had the industry declared them obsolete and systematically eliminated them from production facilities worldwide? The horizontal mill's unexpected revival revealed uncomfortable truths about industrial progress and technology assessment. Morrison's success, replicated by a dozen similar operations across the United States by 1987, challenged fundamental assumptions about manufacturing advancement. The industry hadn't rejected horizontal mills because they lacked capability. The rejection stemmed from incompatibility with manufacturing philosophy that prioritized versatility over specialized excellence. Modern factories optimized for flexibility, machines that could switch rapidly between diverse jobs serving varied customers. Horizontal mills represented the opposite approach: extended setup time, creating capability for sustained production runs. This philosophical mismatch meant that horizontal mills' genuine advantages became invisible to contemporary manufacturing management. The machines excelled precisely where modern equipment struggled, maintaining rigid dimensional relationships across multiple simultaneous operations in difficult materials. But quantifying this capability required encountering the specific problems where it mattered. Most manufacturers never faced such challenges. They produced parts within modern machining centers' comfort zone, experiencing no failures that would prompt reconsidering equipment choices. The jobs that defeated CNC technology represented perhaps 2% of total manufacturing volume, a small enough fraction to be considered edge cases rather than a legitimate capability gap. Morrison's customer base consisted entirely of this 2%. Companies working at the boundaries where contemporary technology's limitations became visible. For them, horizontal mills weren't obsolete, but rather essential tools that modern manufacturing had mistakenly discarded. The economic analysis proved equally thought-provoking. Morrison's equipment. Investment: 3 horizontal mills acquired for under $4,000 total, with restoration costs of $32,000, generated capabilities that new CNC machining centers costing $1.5 million couldn't replicate. The return on investment calculation seemed to violate fundamental assumptions about technology value. Yet the calculation missed critical context. Morrison's business model worked only because he possessed increasingly rare knowledge of horizontal mill operation. His machinists, both in their 60s, represented a dying generation. Technical schools hadn't taught horizontal mill operation in 20 years. When Morrison retired, who would maintain the expertise his business depended upon? The horizontal mills themselves would likely outlast human knowledge of how to use them. The 1898 Pratt & Whitney showed no signs of wear after processing hundreds of titanium brackets and Inconel fixtures. The machine could easily operate another century with basic maintenance. But without machinists, understanding arbor assembly, gang cutter setup, and tramming procedures, the capability would become inaccessible regardless of the machine's mechanical condition. Morrison recognized this approaching horizon. He'd begun documenting procedures in detail, creating training materials for younger machinists willing to learn skills the industry considered obsolete. The work felt like preserving a dying language, valuable but swimming against cultural currents that considered such knowledge irrelevant to manufacturing's future. The 1898 horizontal mill continued running 3 shifts in Morrison's shop, solving problems that modern technology rejected as impossible. The machine represented a question that the industry had answered prematurely. What other capabilities has manufacturing discarded in its relentless pursuit of progress, and what problems remain unsolved because we've forgotten technologies that could address them?